We're going to look at a very special case of homomorphisms. Namely, we're going to look at homomorphisms where the domain is the integers. Okay, so we're looking at how can you send how do the integers interact with other rings via homomorphisms? The theorem is that there is a unique homomorphism from the integers to any ring. So there's one and there is only one. Okay, so one and only one. So this is existence and uniqueness. Now, when you have a ring where there is one and only one homomorphism from U to any ring out there, we have a special name for this. So this is saying Z is an initial ring. And it turns out that any two initial rings are isomorphic, and that is going to be an optional homework problem. But the purpose of this theorem, sorry, not porpoise, is to understand what homomorphisms out of Z look like. So let's observe something. Let's observe that if such a phi existed, then what? Well, we know that phi of 1 has to be the 1 in the ring because it's a homomorphism, and homomorphisms preserve unity, so they send 1 to 1. Well, if we had any natural number then, we can write our natural number as 1 plus 1 plus 1 n times. So there's n of these. And so therefore phi of n, whatever it might be, has to be phi of 1 plus 1 plus 1 n times. But phi breaks up under a sum of two elements. In particular, it breaks up under a finite sum. And each one of those is n. Or sorry, it's 1. So this is the one in the ring plus the one in the ring, and so on. How many ones are there? There are n ones. So we're going to write this as n times 1. And what this notation means here, a priori this makes zero sense, right? Because I have a random ring. What does an integer look like in a random ring? It doesn't make any sense. They're not the right type. But what we'll mean by this notation n times 1 is precisely this. Similarly, if you had n and n, then, well, not all integers are positive, right? Some are negative. So phi of negative n, well, it's a homomorphism, so the negative comes out. And phi of n we just computed. It's negative n times 1r. And that happens to also be negative n times 1r. So you can put the parentheses there if you like. And why can you put the parentheses there? Actually, it's non-trivial, and we would have to prove it, but we're not going to. We're going to gloss over some things here. Okay, so that's all the positive integers, and that's all the negative integers. And then lastly, well, phi is a homomorphism, so phi should send 0 to 0, which is like 0 times 1r. So what we're saying here is that there is somehow what we call an action. There's an action of the integers on this ring R, and what it does to at least to the element 1 is if you have a positive integer, it sends it to that many sum of ones. And if you have a negative integer, it sends it to that many sums of negative ones. Now, one can check with the let me call this star up here. One can check, but we're not going to. But star, actually, with this notation, what we're going to get from this is that if we do n times 1, and we multiply it with m times 1, it's the same as first multiplying nm and then doing that many ones. And this is not hard to prove. You use induction, so it uses induction, but sort of this is an optional topic, so we're not going to go too far into this, but one would prove that with induction. Okay. All right, so one can also see that with this notation, for all n and m in Z, n times 1, I don't need parentheses here, n times 1 plus m times 1 is what you would think it is. It's n plus m times 1. And my point here is, again, one has to prove both of these, but once one proves both of these, is not only if phi exists, it has to do this, but actually this makes sense as a homomorphism. This adding one together n times, or adding negative one together n times. So actually, from these facts, we can learn that the mapping phi from Z to R that takes phi of A and does that many, either if A is positive, adds 1 to itself that many times, or if A is negative, adds negative 1 to itself that many times, or when A is 0 is 0. This is a homomorphism. And why is that? Well, up here I've waved my hands in showing that it's multiplicative. Again, one can use induction. It's kind of involved though. And then we've waved our hands that it's additive. Again, one can use induction. It's kind of involved though. And phi evidently sends 1 to 1, because phi would send 1 to one many unities in R, and that is of course 1 to 1. So not only does, if you had a homomorphism, it has to do this, but this actually also defines a homomorphism. And so that's it. So as an example of this notation, because I know it's a little bit weird, so that's the end of the proof. If it exists, that's the last bit, and is unique because it has to do exactly what we said. As an example of our notation, suppose we were looking at the unique homomorphism by the theorem. There's a unique homomorphism to any ring. And let's look at it to Z mod 3. So what is this homomorphism going to do? Well, it's going to send 0 to 0. It's going to send 1 to the 1 in Z mod 3. It's going to send 2 to the sum of 1 with itself, which is 2. It's going to send 3 to the sum of 1 with itself 3 times, which is 3. It's going to send, which is 0. It's going to send negative 1 to the sum of negative 1 with itself, which is positive 2 rather, sorry. Positive 2. It's going to send negative 2 to the sum of negative 1 with itself twice. So that's negative 2 bar, and that's 1. And it's going to send negative 3 to the sum of negative 1 with itself 3 times. That's negative 3 bar, which is of course 0. So that's what's going on with this homomorphism in the case when the codomain is Z3. Again, you always get a homomorphism. And in this setup, what we're doing is we're saying for any integer in Z, we're setting phi of that integer. We're setting phi of that integer equal to A times 1. But what's A times 1? This is really just A bar, right? And so this is what this map is in this case. This is the reduction mod 3 map. And there's nothing special about 3, but this is what the notation is. So for another example, suppose we had 10. What's 10 times 1? Well, I have to add 1 to itself 10 times. That's just 10 bar. And 10 bar mod 3 is 1. Now, this is just with the modulus of 3, but this works always. You always have one and only one homomorphism. So if we look at Z to say Z6, there exists one and only one homomorphism. The homomorphism is the guy that's going to send an A to the A, well, it's going to send it to A many ones, which is just A bar. So the unique homomorphism in this case is reduction modulo 6. Great. Let's look for a minute, and the last we'll talk about this initial ring Z, is let's look at the kernel of these homomorphisms. In fact, let's look at the kernel in general. So if we have a general N, oops, I don't want to put it there. If we have a general N, the unique homomorphism is reduction modulo n. So what that does is it sends phi of a to whatever happens when you reduce modulo n. Let's look at the kernel and image of this guy. So the kernel of phi is the collection of all integers such that a bar is 0 bar in Z mod n. Okay, so what is that? That's the collection of all integers where a minus 0 is divisible by n. So it's a multiple of n for some k and z. So in other words, it's a collection of all integers where a is a multiple of n. And we have notation for this. We usually call this the multiples of n. So take n and multiply it with any integer. So for example, in the ones we just did, for example, this guy, the kernel of phi is 3z. Because the multiples of the 3 are the guys that reduce, I'm missing a bar here, are the ones that reduce to 0. Similarly here, the multiple of this phi is 6z, because that's what goes to 0. So that's the kernel in this case. Let's look at the image of the reduction modulo n map. And in particular, the image is actually everything. So it's actually Z mod n. Right? It's a subring of Z mod n, and it's actually all of Z mod n. And the reason is because the elements here look like 0 bar, 1 bar, 2 bar, all the way up to n minus 1 bar. And what elements get sent to them? Well, an infinite number of elements get sent to them. Actually, let me write this as a column. Let's write Z here and Z mod n here. So 0 bar, 1 bar, 2 bar, all the way down to n minus 1 bar. So what elements get sent to them? Well, 0 gets sent to 0 bar, 1 gets sent to 1 bar, 2 gets sent to 2 bar, n minus 1 gets sent to n minus 1 bar. And in fact, an infinite number of things get sent to 0 bar, it's nz. And an infinite number of integers get sent to 1 bar, it's everything that has a remainder of 1 when you divide by n, and so on. But in particular, this map is onto, right? Because every element has an arrow on it. So the reduction modulo n map, well, first of all, is a homomorphism. It's the unique map out of Z, and it is onto. So it is an epimorphism. It's even better than a homomorph. Well, it's not better or worse, but it's additionally it's surjective on top of being a homomorphism. Let's notice one more thing. Since our kernel is not 0, we also know that this is not, reduction modulo n is a homomorphism, is an epimorphism, but it's not a monomorphism because it has a non-trivial kernel. Lots of things get collapsed. So it's not a monomorphism, so it's not an isomorphism, so it's not any of those other orphisms. So this is an example of what's called the initial ring. There's other ways of writing Z, and so it's not unique, but there's any two initial rings are isomorphic. Furthermore, we looked at the kernel and the image of the unique map out of Z, the initial ring, into Z mod n, and we saw that it was surjective and has as its kernel the multiples of n.